All right, so we've already covered some of natural language processing, but now we're going to kind of see how we can use it with neural networks in deep NLP. So one of the main ideas is word embeddings, which are basically vector representations of words that allow us to capture semantic meaning. So what this does is basically take a word, turn it into a vector. So in NLP before, we would just have, a single vector and each word would have some number. But with word embeddings, we're actually going to project it into a higher dimensional space where we're actually going to have multiple dimensions, anywhere, from 5 to 100 to 1,000. And what this does is allow us to kind of capture the context and the relation between different words. So this will allow us to understand that man and woman are kind of similar words, but also like opposites. And then also that, king goes with man, but queen goes with woman. And I have a picture here that kind of, let's see. So when we create these vectors, what we would want to happen is basically we would have a man vector, and if we multiply that with a female vector, it would give us woman. And then similar, if we take woman and royal, it would give us queen. So that's kind of how they work. You can kind of see other examples here. It can also learn, verb tenses. Swam and swimming are both similar. They should have similar vector representations. And then also, countries and capitals, things like that. So this allows us to kind of capture the meaning and the context within sentences and kind of learn which words tend to appear around which other words. All right, so we're going to hop right into an example to see how this works. So we're going to load some data here and look at it. This data set is used to classify different news headlines in order to tell whether they're sarcastic or not. So our target is sarcastic. I think 1 means yes, 0 means no. We have our headlines, and then we have article links. So basically the sarcastic ones are from The Onion. If you're familiar with that, it's all like fake news headlines. And then the real ones are just from various real news sources. So this is our data set. So we're trying to take these headlines. We can go ahead and take a look at one just to give you an idea. You can do df.headline. I'll do that one. Oops. So area boy enters jumping and touching tops of doorway phase. That one does not make a whole lot of sense, so that's probably sarcastic. Let's find like a good one. 60 journalists killed in 2014 as targeting of international press rises. So that one obviously sounds real. So that gives you an example of what they look like. They're not very long, a few words to like maybe up to 20. All right, so we need to set basically what we're going to call our corpus, which is our kind of dictionary or list or collection of our different headlines. And then we want our sentiments, which is our target. So we're just going to store those here in those objects. And then we can also look at the ones in the corpus by indexing it like this. All right, so now we're going to tokenize the corpus, which if you remember from the first NLP lesson, that's basically breaking it down into a list of individual words. So let me find my annotate thing. So basically, we have a sentence, the summit went well. So it would basically break it down into a list of individual words, all as individual strings. So that's kind of what tokenization does. If you use this built-in one in Keras, it's pretty nice. It actually does some stripping of, like non-word characters, like symbols and stuff. And there's a lot of parameters you can change around with it, but we'll just kind of keep the default for now. So you create an instance of it, and then you can fit, you do fit on text, and you pass in your corpus. And then what this next part does, so actually if we comment this out first, run it, and then we're going to check how many unique words we're going to end up with. So I think it's like this. I have to exit out here. Okay, so we would have 30,884 unique words, which that's going to be a lot. As some of you saw with neural networks, when we get into large data spaces, it's really difficult to run them in like a short amount of time. It's going to take a lot of computational resources. So what we're actually going to do is limit it to the 1,000 most common words. So basically this will only look at the most common words and use those to determine whether it's a sarcastic headline or not. So we'll go ahead and run that, and then we'll go back into here. If you do this word index, it basically gives you a dictionary of all the words, and then I believe this is just their index, which is usually their count or their occurrence. So all the words have a different value. Now we need to set our vocab length, and we actually set it as our number of words plus 1. This is because the Keras tokenizer, it skips index 0 and allows that to be its own thing, kind of as a placeholder. And also if you want to kind of pad your inputs, which we'll see in a second. So we just have to add 1 to that, and that gives us our total vocab length. And now we're going to encode the corpus. So we're going to take it from the words and convert it to the numbers, the numerical representations. And you do that with text to sequences, and you just pass in the whole corpus. So we'll do that, and we'll get a list of numbers. So each of these are the headlines and then the encoded values for each of the words within them. So now we have everything.
Can I ask a question?
Sure.
So the first one, they encoded the first item in the list. That's like a 3 words item, right? Like 354, 266. But when I check corpus, the headline is not 3 words. Does it mean that?
So it's going to be this one. So basically it's taken out words that aren't in the 1,000 most common.
Oh, okay, that's why.
So it's just going to ignore those because we're not going to train on all the 30,000 or whatever.
Okay,
so yeah, so that one, like 30 something, like that's probably not very common. Maybe Doomsday is, I don't know, but there's only apparently 3 of those 1,000 words within that first one.
So when you select the first 1,000, it default the most common?
Yep.
So the index is actually reverse of the occurrence, right? Because the first index is 2. Does it mean that it occurs the most?
So I think like the lower the number here, the higher the occurrence rate is.
The lower the index, the higher. Yeah.
You can kind of see that, like homunculus has a pretty high number. That's going to be a rare one, but something like United is actually going to be within our 1,000.
Okay, thank you for explaining.
Yep. All right, so we have our encoded corpus. Now we need to find our longest review. So all of our inputs have to be the same length. So we need to figure out what the longest one is first. So we just do that by finding the max length of all of our reviews within our corpus. And we notice that it's 62. So now we have to pad all the other reviews to also be 62 length. And basically what this does, pad sequences, it's going to add zeros to all the reviews that don't meet the 62 length. it'll bring them all to 62. The parameter in here, padding, padding equals post means it'll add it to the end. You could also do, I think, pre, and it'll add it to the beginning. But in this case, it makes more sense to add it to the end because it's kind of just, blank space. So if we run that, you can kind of see that here. A lot of them are going to have zeros on the end. So basically, those aren't really going to carry any weight in the network. It's only really going to focus on the ones that have actual values. But this way, all of our inputs are the same length, so it'll work well with the neural network. All right, so now we're going to do a train test split. Like usual, we're passing in the padded corpus and then our sentiments. And now we're going to build the model. It's going to be a pretty simple one. Usually when you work with NLP like this, you're going to end up with a lot larger networks, but we want something that's going to be easy enough to run right now. So we create our sequential object, and now the first layer is going to be our embedding. So this is going to take our inputs that are just one number for each word, and it's going to project it into a higher space, and it's going to be 50 dimensions. So we're going to go from 1 dimension for each word to 50. That's what the second number represents. The first number is just going to be the total number of unique words, which is our vocab length. And then our input length is that longest review length, the 62 that we found. So that's kind of all you need for embedding. There are other parameters to mess with. We can go into the documentation and look at. But for now, this is all we need. And then since we have 50 dimensional vectors, we need to flatten them afterwards. And then we're just going to pass it all through one large dense layer of 500 neurons. And then our output is just going to be a single neuron with the sigmoid. Since it's binary classification, it's either stochastic or not stochastic. So we'll go ahead and run that. Does this architecture kind of make sense to everyone?
Can you explain the 50 part again?
Yeah, so the 50 is basically how large of embedding space we want. So like I said,
what does that mean?
So like one of our words right now is just, a single value. But once it goes through the embedding, we can make it any dimension, any size of dimension. In this case, it's going to be 50. So now it's going to have 50 different values for each
Why
word.
we want it to be 50? Like, what's the intuition behind this?
Because it's kind of like those first pictures I was showing, that will allow us to kind of project all our unique words out into, think like this big cloud, and words that are similar in meaning or use might be in similar like locations within that cloud. Because if everything's just one value on a line, it's kind of hard, to separate and to kind of clump similar words together, words that are usually used in the same context. So when we put it in 50 dimensions, we can really space them out. One dimension might represent like animals. So like all animals would have a high value in that dimension. Another might represent cities. All cities will have a high value in that dimension. Does that kind of make sense?
So tie back to the neural network we learned earlier, is that number of features or?
Yeah, so it's kind of like number of features, but it's dimensions. So when we go to the summary, I think if that's the next part, yeah, this might. So our inputs are going to be 62 words, and each word has 50 dimensions coming out of the embedding layer.
Okay, each word, okay.
Yep. And then since this is, not flat, we have to flatten it. So then we end up with this many parameters, which is a lot. And that's why we do 500 neurons to kind of ease that down, since our final one's just going to be 1. Really, You'd probably want more. You'd probably want like 1,000 and then maybe another layer, but we're trying to just keep it simple for now. So we'll keep it at that. So yeah, you can see kind of how many parameters we have. It's a lot since we did go up to 50 dimensions. You can always try changing this, especially if it's slow on your computer. If you lower the embedding space, it will run a bit faster. So something to keep in mind.
And Matt, what's the none, Roseanne?
Which part? The none?
Yeah.
So we're not telling it that we're sending in any specific number of samples. So this would be like how many batches, like how many headlines we're setting in at one time. So by not giving it one, we allow ourselves to pass in any number. So we can set the batch size later and it can accept any value there. All right, so now we're gonna fit the model and train it. So basic stuff here, optimizer, atom, loss, binary, cross entropy, and we're gonna look at accuracy. And then we're gonna fit on the train, pass in the validation. You might wanna change this here. My computer can do this batch size of 512. Yours might not be able to, or it might be too slow. So you might have to change that around. But number of epochs should be fine. So we'll go ahead and run this. All right, so after 10, well, we can see that it learned really quickly. Basically, after the first one or two, we already hit the maximum, and we actually started to lose some validation accuracy as we went on. So we definitely probably would have wanted to stop it earlier. There's definitely some tuning we could do with the architecture to get this number a little bit better, but you can see that's still pretty good for training that quickly. 80% accuracy on the test. That's kind of the power of the embedding layer. If you tried to do this without that, you wouldn't be able to get anywhere near that kind of accuracy. So yeah, so that's one example. That was using our own embeddings from scratch. But what you can actually do is use an embedding layer that's already been trained by someone else, and basically just load that in. And then you don't actually train that layer. You just use the weights. You learn the meaning and context that they've learned in theirs on your own data set. So there's two main options for this. There's word to vec and glove. They're both kind of similar. They're both word embedding weights, but some of them work better with certain data sets. They have different implementation ways. So like glove we can do in Keras pretty easily. Word to vec, we have to import this other library called gensim. It's a little more complicated. I think word to vec is probably more popular now, but glove is still used a lot. And so if we take a look here, all right, so there's a few different options. We downloaded the smallest one, so it's trained on, let's see, 400, it's this one here, the first line, 400,000 words, 6 billion tokens, and then they have 50, 100, 200, and 300 dimensional vectors. So that's like embedding layers. That's how many dimensions. So we actually got the 50, the smallest one. But you can see it can go up to a 2.2 million vocab. And they have these other data sets. The last one came from Twitter. You'll see these a lot, especially like on Kaggle. It can save you a lot of time because you don't have to train that part of the network. But this also kind of explains a little bit of how the embedding layers work and stuff like that. It's pretty cool. So if you downloaded that file, you'll just want it in the same folder as this notebook. And then we're going to use this function that basically reads that file, and it's going to create a dictionary for us of all the words in it, and then their basically weighted value for the embedding layer. So we'll run that. And then you'll want to just declare the file here. It should be the same name as this. And then we'll go ahead and load it. It'll probably take a little bit. It's a large file. All right, so it loaded 400,000 words. So now we have to get the weights for all the words that are in our headline data set. So we're going to create our embedding matrix. It's going to be a matrix of zeros that has our vocab length, which is like 1001, and then the 50 embedding layer dimensions. And it's just going to be all zeros. And then down here, we're going to set each individual one. So we're going to go through all the unique words that our tokenizer found. And if the word isn't within that first 1,000, we're just going to skip it. That's what this part does. Then we're going to get the glove vector, the value of that from the dictionary, passing in the word. And then if the word wasn't not in there, because sometimes you'll have words that aren't in that glove dictionary. So if it's not in there, then we'll just set the value at that index to that embedding vector. So this basically just grabs all the parts of the glove data set that correspond to the words that we're actually using. I'll run that. We can take a look at it. So this will be basically 1001 vectors that are 50 dimensions in length. All right, so we're going to use almost the same architecture as before, but this time in the embedding layer, we're going to set the weights equal to our embedding matrix, because that's what those values are here that we created. So we're going to set the weights, and then we're also going to turn trainable to false. So this means that it won't actually do any training on this layer. It'll just use the weights it has, pass them through, and it'll train the rest of the network. So we'll go ahead and run that. You can see the summary looks kind of similar. And then we're going to train it. All right, so after 10, it looks like we do have a little bit worse accuracy on the validation, but it does seem to still be increasing, so we could probably train this a little bit more. But it is still kind of similar to without the glove. It's not something where it's always better to use it, it's just sometimes it does give you better results, and sometimes it just is easier to run. It's less computationally expensive. So you don't have to use glove, but you should probably try it out if you can, just to see if you still get good results with it, because it's a lot easier to run. So that's kind of how you would load weights like that. Word2Vec is kind of similar. You're going to have almost the same thing once you get to this step. It's just creating this embedding matrix is a little bit more complicated, but there's some guides for that that you could always look at if you wanted to go that route. And you can always use one of the larger data sets from Glove. It'd probably give you better results if you had more of the words or higher dimension vectors. So yeah, so that's using pre-trained word embeddings. All right, so for this next part, we're going to talk about long short-term memory networks, or LSTM. So anytime you see LSTM, you should immediately think NLP. This is a specific type of neural network layer that is used almost extensively with NLP. It can also be used for time series data though, because what it does is take into consideration basically previous values and inputs that it's seen. So I have a YouTube video here I'd recommend watching. It's about 10 minutes long. The math for LSTMs is really complicated. It is outside the scope of our time tonight. So I'd recommend diving into this if you want to understand it a little bit better. But just to give you an idea of what it does, I think I liked this example here. So say we have a customer review of the cereal. We have this little paragraph here about it. You know, I think it's amazing, blah, blah, blah. But when we read this, we don't really look at each word individually. We kind of pick out the important words, like what this says here. So like amazing, you know, they said perfectly balanced, we'll definitely be buying again. So those kind of are what we hone in on and allow us to determine, you know, whether this is a positive review or negative review. So LSTM layers basically do this. They learn basically what pieces of the input are most important and focus on those. This gives like probably the best results possible for NLP stuff. You'll basically see LSTM layers in almost every single NLP network. They are, however, highly computationally expensive, more so than the embedding layers, but they work really well. So we'll go ahead and go into an example to use one. So our goal, and this is also kind of a showcase of one of the applications of it, where you can use an LSTM network to actually generate text. So we're going to take in a data set of Trump tweets, and we're going to generate some of our own. So we're going to load in the data set here. We have a bunch of stuff we don't really need, like date, time, the type of it, whether it was, you know, a photo, retweets, all that. We're only going to be concerned with the actual text of it. So we will go ahead and grab that, and then we're going to do a little bit of pre-processing here. So what this first part does in here, it basically looks for any links that start with, you know, HTTP or HTTPS and removes them. Because if he tweets a picture or a link to anything, that'll be included, and we don't really want to train the network on those. So we'll go ahead and remove those, and then we're also going to make it all lowercase. There's other pre-processing you could do for sure. You could remove certain symbols. You could do stemming or lemmatization, but for now we're just going to do this. And then we're going to do something different here, where at the end of each tweet, we're going to add this word end of tweet. Because basically what this will do is give us basically a stop of the tweet, so that when we generate them, we know when we'll get, like, you know, an actual tweet. It won't just be like a paragraph that'll go on and on. We can make the network learn cutoff points of when a tweet would end, basically. So that's what that does. It goes through each of the tweets, does that pre-processing, and then combines it into the corpus. And we can take a look at it here. I think you can see a couple examples where it missed a link or two. So there's definitely more pre-processing. You know, we still have hashtags in here, which we maybe want to include, because if we want to recreate them, we might want to still include those. But there's like new line symbols. So this isn't going to be perfect. There's definitely a lot more we could do, but we'll see what kind of results we get with this. So we're going to fit a tokenizer to it. We're going to limit it to 2,000 words. It's just kind of the number I found messing around with it. You can try different values, but we would normally have 8,104. And the other thing back here, we actually are limiting it to 5,000 tweets. We definitely have more than that, so you could change that too, but just to keep it a reasonable size for training, I did 5,000. All right, so then we're going to encode it like before. We get all of our numerical vectors. And now this part, so the idea, how we're actually going to generate it, our inputs are going to be 3 words, and then our target is going to be the 4th word. So if we have a sentence, like say this is our sentence here, we're going to break it up. So our first X is going to be this, and then our first Y is going to be this 4th word. Then we're going to move down. So we're going to take these 3 words, and then our Y is going to be this word. So we're going to kind of move down each tweet. Each of our inputs are 3 words, and then the target is the next word or the 4th word. So that's basically what this cell does here. It loops through if we're at least the third word, then we kind of grab from our index, basically 3 spots before it up to the index, and then our y is going to be at the index. All right, so that will create our x and y. And the other thing, you can change this value. You could do 2 words and then the third, 1 word, and then the next word, 5, and then the 6th one. You can kind of try out different things. Another thing that works is you can actually do this on the character level. So you could break every tweet down into individual letters, including spaces, and then you train it on maybe, 3 letters, and then it predicts the 4th, which you would think maybe wouldn't work so well, but it actually does. It'll actually learn to produce actual English words that are spelled correctly and everything, which is pretty cool. So that's something else we could try later. But for now, we're going to do it this way. So we have our x and our y. We have to do a little bit of changing the shape of them. So we have to make our x a NumPy array, and then we just have to reshape it to get it to be the right size for the neural network. And then our y needs to be categorical. So it's basically going to be an array the size of our vocab, which is like 2,000 words. And then, it's going to be all zeros with a 1 at the correct word, like so. And then we're just going to do, a train test split, like usual. All right, this is the network. Again, it's going to be somewhat simple. So we have an embedding layer, and we're going to have 2,000 for our vocab. And then our output dimensions is going to be 100. That's basically how many embedding dimensions we're choosing. And then our input length is 3, because we do the 3 words, predict the 4th. The LSTM layer is really easy to add here. We're not going to do too much with it. You usually want to do like 64, 128, or 256 on this. And you can actually double them up. You could have a second one afterwards, but you have to set on the first one, I think it's return, it's going to be return sequences equals true. That will allow you to pass it to a second LSTM. But that's going to increase the time it takes to run this, so we're just going to keep it at 1. And then we're going to put it down to a 500 dense layer, and then our output is going to be the same as our input. So it's our vocab size of 2,000 words. And I'm missing a parenthesis. There we go. So that's what it looks like. You can see a lot of parameters. So it's definitely going to take some time to train. But you can imagine if we increase the size of this at all, how big the parameter size would get. All right, so now we're gonna fit it. Again, you might have to mess around with the batch size to find something that works, and also the epochs. I'm just gonna do 40 for now. We'll see kind of what we get. This will take a little bit longer than the first example to train, I think. And this is a good example because it's going to look like it's not improving for the first couple epochs, but then we'll see that it does start to improve. So that sometimes happens with neural networks. It might seem like it's not doing anything, but then it'll kind of pick up. So we can see our train accuracy kind of in this column is increasing. Our validation accuracy is over here, so like 18. It's not increasing as much, so it's definitely not performing the best, but it's still going up. We're at 19% on the test. Hopefully everyone else is able to run this not too slowly.
Way slower than yours.
Yeah, it's taking a while.
All right. Well, basically the test kind of plateaued at about 18 or 19. That's where I stopped it. So you may think, oh, this is really bad accuracy, 37 on the train, 18 on the test. But this is a little bit different than when we're classifying something. We actually don't want perfect accuracy here. We don't want it to just recreate the tweets that we passed in. We want it to create new tweets. So we do want it to kind of get things wrong sometimes, but it's kind of finding that sweet spot where it doesn't recreate exact tweets that have already been made, but it creates believable ones that are different enough, if that makes sense. So there's a lot more to mess around with like generative models like this, but we'll kind of see what this ended up doing. So this will generate new tweets. So you have to pass in a seed set of 3 words to get your initial prediction. And then from that, it'll just keep predicting words. And that's basically what this does. If we get that end of tweet word predicted, we'll just stop because that says, the tweet's over. And then all this does is basically, like we have our words here, and maybe this is our 4th word. So then our next set of 3 would be here, and then we predict the next 4th word, and it basically keeps shuffling down. That's what this part here does. And then we just keep a running, basically, list or string of all the words so that we can print out the tweet at the end. So we'll go ahead and run this. So I am very proud of you. Okay, proud of who? That doesn't make a lot of sense. One that I found that was funny was, let's see, Obama was a disaster for president. Okay, that sounds pretty realistic. Clinton is a disaster. Try using your last name. So this is really fun to play around with. If you can get yours trained, definitely put a bunch of stuff in. It won't always make sense. Like I am the only one who started off the hook. Not sure what that means, but I think the obvious one, make America great again. I got that right. So definitely something fun to mess around with. It's one of those things where it's never perfect. We're not predicting something that we have to get right. So it's kind of like you have to do a lot of testing to see if it's believable or not. And then to give you one more example of this, because this stuff is fun, this is something I made. It's basically a lyric generator. It'll take a second to load up. I hosted this on Heroku, and for some reason, the first time you load the website, it takes forever if it hasn't been loaded in a while. All right, so this is my lyric writer. So I trained it on the top female queens of pop music, and you basically enter one word for inspiration, and then you can kind of choose the originality. So we'll do somewhat original. And then basically generates a whole song. So verse, chorus, bridge, chorus. And it actually tells you which artist contributed to those lyrics and what percentage. So pretty fun. It'll give different results each time, even if you put the same thing.
This is great.
Yeah, this is really fun to make. It was also a headache, but. And actually, so in our example here, we get the prediction it makes every time. So basically the argmax. But what I ended up doing is using kind of added a random factor. So it doesn't always pick the one that has the highest value. It basically uses all of the predictions as weights. So it makes the one with the highest value more likely, but it won't always be picked. Because sometimes what you can run into, I don't know if we can make this happen. Let's see. I am Donald. No, that didn't work. Maybe if we take this out. Oh, that'll do 1,000. I don't want that. We'll do 128. Yeah, so sometimes, see, like it'll keep doing the same word or the same phrase over and over. So sometimes you have to add something to kind of break that up. But in this case, I guess it makes sense because the tweet's over, so it's going to keep predicting that. But yeah, so that's a generative model. So before we get to the activity, does anyone have any questions or comments on that? All right, so this activity is a little bit different. You actually have a choice of 2 different options. And this is kind of going to look like a mini project, but you don't have to take it that seriously at all. The goal is just to get a model working. You don't have to worry a whole bunch about pre-processing or making it look pretty or anything. The goal is just going to be to practice bringing in text data and basically putting it into a neural network. So you can either do a classification task. This is just on Kaggle. It's basically toxic comments online, determining whether a comment's toxic or non-toxic. So that can be fun. And the second is to use a book from Project Gutenberg, which is like an open source collection of books. You can go to it here. So it has a bunch of old ones, you know, things that are open source now, but has like Alice's Adventures in Wonderland, Charles Dickens stuff. So some classics, but basically use one of those and build a generative model that can basically write, you know, new chapters to the book. So those are kind of the 2 options. There's definitely examples online of how to do both of these if you get stuck. But I thought it'd be fun to give you kind of a choice and kind of something to have like creative choices on. So yeah, so that's the activity. Let's see, how many people do we have?